Jumping back into our gas laws, we're going to practice some calculations on our four basic gas laws, which are Boyle's law, Charles' law, Luzak's, and Avogadro's laws. Boyle's law was pressure and volume. Charles' law was volume and temperature. Luzak's law was pressure and temperature. Avogadro's law was moles and volume. Boyle's law is the only one that's really different from the other ones in regards to its formula and its setup and the relationship. That's because it's an inverse relationship. If one of the variables goes up, the other one goes down, and vice versa. So that's to say, if you increase the pressure of your system, your volume will decrease. Charles' law, Luzak's law, and Avogadro's law, they're all direct relationships. If one variable goes up, the other variable in turn goes up with it, or vice versa. That's like in Luzak's law. If you increase the temperature on your system, the pressure will go up with it, or if you decrease the temperature, the pressure will go down in turn. So these are the four formulas that we will be using for our practice problems. Which formula you use is determined by which variables you have set up in the problem itself, and that's part of figuring it out. So with that said, let's just jump straight into it. Alright, so our first problem says the temperature inside a refrigerator is about 8 degrees Celsius. So if you want, you go ahead and start picking out information and writing it to the side. That's what I like to do. So I got a temperature at 8 degrees Celsius. Now one thing I know is this temperature has to be in kelvins, which we'll take care of that in a minute. If I place a balloon in the fridge that initially has a temperature of 30 degrees, alright, so I got a second temperature, and that's of the balloon. So this is going to be 30 degrees. Now I need to label these two temperatures. So this 8 degrees is the temperature inside the fridge, so I'm going to call this TF for temperature fridge. And 30 degrees is the temperature of the balloon, so I'm going to call that TB, just for now. And it has a volume of 0.7 liters. So volume of that balloon is 0.7 liters. What will be the volume of the balloon when it is fully cooled to the temperature of the refrigerator? So I'm looking for a new volume. I'm looking for that second volume. Now, these two variables here, they will go together. The temperature of the balloon and the volume of the balloon originally. So I'm going to change that B. I'm going to change that to a 1 now, just so it's indicated as my original. And it says we're going to change the temperature, the final temperature of the balloon to that of the refrigerator. Well, the refrigerator temperature is 8 degrees, so I'm going to change this to temperature 2. Alright, next thing I need to do is convert these degrees Celsius to kelvins, because our formulas can't use degrees Celsius. So the way you change Celsius to Kelvin is very simple. You just add 273. So 273 plus 8, it's going to be 281 kelvins. 30 degrees plus 273 will be 303 kelvins. Now we set up our formula. It was volume over temperature set equal to the second volume over temperature. Now just plug in. So volume 1 is 0.7. Temperature 1 is 303. Volume 2, so I'm looking for, that's going to be X. Temperature 2 is 281. That's what I'm changing it to. Solve this out, we just cross multiply, then divide. So 303 times X is 303X. 0.7 times 281 is 196.7. I divide by the value with X, so 303 cancels. 196.7 divided by 303, and I get 0.65, 0.65, but I need a unit. Since I'm looking for volume, and my original volume was in liters, that makes this also liters. Those units have to be consistent, so there's our answer. Sometimes a problem may ask you to identify which law this is. Since we use volume and temperature equals volume and temperature, this is going to be Charles' law. Sometimes it'll ask, sometimes it won't. This one in particular did not, but we just identified it just for good practice. All right, next problem. If 50 moles of gas are in a 50-liter container at 450 kelvins, what is the temperature inside the container if the volume changed to 30 liters? All right, let's pick out our information so we can determine which law it is. So I got 50 moles. I got 50 liters. I'm going to call that V1 since it's just the first volume I see. And that first volume is at 450 Kelvin, so I'm going to call this temperature 1. It's 450 kelvins. So we got 50 moles and 50 liters at 450 kelvins. What is the temperature? So I'm going to change the temperature. I'm looking for the change in temperature inside the container if the volume changes to 30. So we're changing the volume here to 30 liters. Alright, nowhere in the problem does it say the number of moles has increased or decreased, so we're going to assume it stays the same, so that means we're technically just going to ignore this information. We don't need it, it's constant. So I'm dealing with volume and temperature again. Volume and temperature is Charles' law. So I'm dealing with Charles' law again. That's going to be V over T is equal to V2 over T2. Now we just plug in our numbers. So V1 is 50 liters over temperature 1, which is 450. V2 is 30 liters. And T2 is X. So 50 times X is 50X. 450 times 30 is 13,500. We divide by the value with X. 50 cancels. 13,500 divided by 50, we get 270. But 270 what? Well, we're looking for temperature, and our original temperature was in kelvins, so this one will also be in kelvins. There's our answer. Alright, next problem. A gas sample in a 20-liter container exerts a pressure of 760 millimeters mercury. So I got a volume and a pressure. My volume is 20 liters. My pressure is 760 millimeters mercury. These two values go together, so I call this volume 1 and pressure 1. Calculate the pressure exerted by the gas if the volume is changed to 35 liters at a constant temperature. So I'm calculating pressure, so I'm looking for the new pressure, so I don't know what that is. Exerted if the gas is changed to a volume of 35 liters. So we change the volume to 35 liters. We're going up from 20 liters. These two values go together, so I labeled them pressure and volume 2. Pressure and volume means Boyle's law. Again, the problem didn't ask for which law, we're just identifying just for good practice. So Boyle's law formula is P times V, and those are the originals, equals P times V, which those are both the second. Now we just plug in. Pressure 1 is 760, volume 1 is 20, pressure 2 is what I'm looking for, that's X, and volume 2 is 35. So now I just do a little bit of algebra. 35 times X, that's 35X. 760 times 20, 15,200. Divide by the value with X, 35 cancels out. 15,200 divided by 35, get 434.3. Now I need a unit. We're solving for pressures, and my last pressure was millimeters of mercury, so this is also millimeters mercury. There's our answer. Alright, how many moles of air were added to a 125 liter balloon with 10 moles of air if the volume changed to 300 liters after the air was added? Alright, so let's pick out that information. How many moles of air were added? So I'm looking for moles. It says we added it to a 125 liter balloon with 10 moles. So I got a volume at 125 liters when it had 10 moles of air. These two values go together, so I'm going to call this V1 and N1 because that's my originals. That makes this N2. If the volume changed to 300 liters, so my volume changed to 300 liters because we added air, and I'm looking for how much air did I add there. Now, one important thing about this question, it says how many moles of air were added. So once we get to the end of this problem, we'll have an additional step. Well, let's just do the first part to get started. So this is Avogadro's law. I know that because I got moles and volume. So Avogadro's law is moles over volume set equal to the new moles over the new volume. So let's plug those values in. So N1 is 10, V1 is 125, N2 is what I'm looking for, V2 is 300. Cross multiply, 10 times 300 is 3,000. 125 times x is 125x. Divide by the value with x, 125 cancels out. 3,000 divided by 125. So x is 24, and that's going to be 24 moles. So that means at 300 liters, our mole count is 24. At 125 liters, our mole count was 10. But the question asks how many moles were added. So it's not looking for the final amount of moles. It's asking how many moles were added to the existing moles in the balloon. So we do a difference there. So if the final amount is 24 and the initial amount was 10, just subtract the difference. So 24 minus 10 says 14. So we added 14 moles to that balloon. Our next question. How hot will a 750 milliliter balloon have to be in order for it to expand to a volume of 3 liters? Assume the initial temperature of the balloon is 25 degrees. Alright, let's pick out some information. So I got a volume of 750 milliliters and it expands to 3 liters. First thing I instantly see is these two units are not consistent. I need to change one of them. Personally, I prefer to change milliliters to liters. It's pretty easy. So I'm going to erase this M. I'm going to leave it as an L. Now to change milliliters to liters, just move your decimal 3 times. So your decimal's at the end here. So it goes 1, 2, 3. So 750 milliliters is 0.75 liters. Now my units are consistent. So the temperature initially is 25 degrees Celsius. And we're looking for the final temperature. So this will be temperature 2. That makes that temperature 1 since it's initial. So now we got two volumes. We got to figure out which one is the first and which one is the second. So initially the balloon was at 750 milliliters and we changed it to 3 liters. So this is the first volume. This is the second volume. Next I got to make sure to change this temperature to Kelvin. So I add 273. So that's going to be 298 kelvins. And since I'm dealing with volume and temperature, that's going to be Charles's law. That's volume over temperature initially is that equal to the volume and temperature after it changes. So my initial volume is 0.75. My initial temperature is 298. My new volume is 3. And I'm looking for the new temperature. So that's x. Now we cross multiply 0.75 times x. 0.75x. And I got 298 times 3, and that gives me 894. I divide by the value with x, that cancels. So 894 divided by 0.75, get 1,192. We need a unit since we're looking for temperature, and my temperature initially was in Kelvin. This will be Kelvin, so it's pretty dang hot. Alright, next problem. What is the pressure inside a canister when it's heated to 100 degrees Celsius? Its original conditions were STP. Alright, so that's a new phrase, STP. What does STP mean? Well, STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, which is 273 kelvins. Standard pressure is 1 atmosphere. So there's your STP. Let's read the question again. What is the pressure inside a canister when it's heated to 100 degrees Celsius? We're looking for P2. We're looking for that change in pressure. So this is going to be P1. And it also says its original conditions at STP. So these are no doubt the initial or the first pressure and temperature. We heated it to 100 degrees Celsius. So we got to change that to kelvins by adding 273. So 373 Kelvin is my temperature 2. Now pressure and temperature, that is Gay-Lussac's law. And that is pressure over temperature initially equals pressure over temperature after it changes. So P1 is 1 atmosphere. Temperature 1 is 273 kelvins. Pressure 2 is what I'm looking for. Oop. Messed up my formula. Let me fix that real quick. This should be a temperature 2. My mistake. Temperature 2 is 373. Cross multiply 273 times x is 273x. 1 times 373 is 373. Divide by the value with x. 273 cancels. 373 divided by 273, and I get 1.4. 1.4 what? Well, we're looking for pressure. Our pressure was an ATM, so this is also ATM. There's our answer. If the volume of a gas at 5 atmospheres is 750 milliliters, then what will be the pressure at 1.5 liters? Alright, let's pick out that information. So the volume of a gas at 5 atmospheres is 750 milliliters. So I got a pressure at a volume. So these two go together. So I'm going to call that pressure 1 and volume 1. So 5 atmospheres at 750 milliliters. What will be the pressure at 1.5 liters? So I'm looking for a new pressure when it is at 1.5 liters. Now these two units are not consistent, so I got to convert one. I prefer to change my milliliters to liters because you just move that decimal 3 times. So 750 becomes 0.75. And I take off the M from my unit. Now it's liters. Alright, so pressure and volume, this is Boyle's law. And that's going to be pressure and volume originally set equal to pressure and volume after it changes. So pressure 1 is 5, volume 1 is 0.75, pressure 2 is what I'm looking for, and my volume is 1.5 now. So 5 times 0.75 gives me 3.75. Set equal to x times 1.5 is 1.5x. We divide by the value with x, that cancels. 3.75 divided by 1.5 gives me 2.5. But 2.5 what? Well, I'm looking at pressure. Our last pressure was in atmospheres, so this 2 will be in atmospheres. There's our answer. So that's our 4 basic gas laws. Always practice your work. For these calculations, it's very beneficial to just practice so you can get better at it. And I hope this video helped. And as always, good luck on your tests.